So looking at lesson 4.8 on analyzing graphs of polynomial functions. We're going to have a lot of vocabulary today, looking at some models of graphs on the calculator and how to glean information from those graphs to answer some questions. So graphing polynomial functions, we've learned that zeros, factors, solutions, x-intercepts are all closely related. We have this box that says let f of x equals, and then that is a polynomial function. And then the following statements are equivalent. 0, k is a 0 of the polynomial function f, and then x minus k is a factor of the polynomial f of x. Solution, k is a solution or root of the polynomial equation f of x equals 0. X-intercept, if k is a real number, then k is an x-intercept of the graph of the polynomial function f. The graph passes, graph f passes through k comma 0, right? So that's the factoring, zeros, solutions, x-intercepts are all related. We've talked a lot about that. So if I have this function, f of x equals 1/6 times x plus 3 times x minus 2 squared, right? My first reaction is going to be to use Desmos, right? I am going to plug that into Desmos. So I am going to pull up Desmos. And I'm going to enter that function in. F of x equals, and then 1/6 times x plus 3 times x minus 2 squared. So what I can do is start looking at this graph, and I see intercepts here, right? That is where it touches or crosses the x-axis. I see a y-intercept here at 0, 2, and then I see this local maxima here. And that's an important point, right? It's a local maximum, and then this second y-intercept would also, or x-intercept, sorry, would also be a local minima. So what I can do is start to pull that information from the graph and put it into the table if needed, or graph if needed, and then start answering some of these questions. Right, so using my data from Desmos, I can start to kind of fill out this table, right? So I know that I have a point at 0, 2, and I know I have a point at 2, 0. I know I have a point at -3, 0. And then I know I have this local maxima here, right? So I can use those points to build my graph, but ultimately I can answer these questions, these 3 questions, based off my graph in Desmos. So end behavior, what is the graph doing as x approaches -infinity? So as x approaches -infinity, f of x does what? What is my output doing? Well, it's going down, right? So f of x approaches -infinity also. And also then as x approaches +infinity, going up this way, right? What is f of x doing? What is my output, my y value doing? Well, x is approaching +infinity as well. Wants to know the y-intercept, right? That's this point right here. So it is at 0, 2, right? Which also would have been in my table. And then my zeros, right, are defined in Desmos for me as well. It has zeros at -3, 0, and 2, 0. Right? Some people would just say the zeros are at x equals -3 and 2. Okay? So, right, remember this would also be solutions is another word we could use here. We could use x-intercepts. Those are some other vocabulary words that are interchangeable for that one. Right, so finding all real zeros of that function, I am going to simply enter that into Desmos. So let's get this entered into Desmos. F of x equals 6x to the third. Right, and I used my caret button to make this exponent here. Plus 5x squared, so caret 2, minus 17x minus 6. Right, before I start looking at the graph, it's always important that I check my work, that I have typed everything in correctly. 6x to the third plus 5x squared minus 17x minus 6. Right, because one missed sign is going to change this whole thing. Right, so I am going to use my mouse then, and I'm going to tap those zeros, right? These are my zeros right here. I have those 3 points are my zeros where the graph crosses the x-axis. So I see then that I have zeros at x equals -2. So I have x equals -2, x equals -1/3, and x equals 1.5, right? I got that all from my graph. So x equals -2, comma, -1/3, comma, and 1.5. Or 3/2 would work as well. Right, so I have those solutions. And again, I just gathered that information from the graph. So here we talk about turning points. Another important characteristics of those graphs of polynomial functions is they have a turning point corresponding to a local maximum or local minimum value. Right, so local meaning we recognize that the graph may go on to positive or negative infinity, but we see that turning point where it changes from increasing to decreasing, or decreasing to increasing. Either way, we get that turning point, right? The top of the roller coaster, bottom of the roller coaster. That gives us our local maximum or local minimum. Sometimes you might refer to hear those referred to as local maxima or local minima. Same thing. Okay. So the y-coordinate of a turning point is a local maximum of the function when that point is higher than all other nearby points. Right. So this one right here, local maximum would be this one, and local minimum would be this one. Right. A local minimum is turning point of the function when the point is lower than nearby points. Turning point of the graph of a function is a point on the graph at which the function changes from increasing to decreasing or decreasing to increasing. So for example 3, I went ahead and graphed the f of x equals x to the third minus 3x squared plus 6, right, because that is where we're going to get our information. We are asked to identify x-intercepts and the point where the local maximum and minimums occur, and then determine intervals for which the function is increasing or decreasing. Right, so I did not click my x-intercept. It only has 1 right there. But if I did, it would have told me that that 0 come on, that 0 was at negative 1.20, comma 0. And then I have local maximum and local minimum. So my local max is this point right here, right? Because it reaches, it's coming up from negative infinity here, right? And it peaks at 0, comma 6. So it has that local maximum at 0, comma 6, and then a local minimum at this 2, comma 2, right? Because it reaches that peak and then drops to a local low point, 2, comma 2. Those local min and local max determine, they're the changing point between increasing and decreasing. So I'm going to write these increasing and decreasing intervals as inequalities, right? So when x is less than this 0, it's increasing. And it's also increasing when x is, and then again at when x is greater than this 2, right, from right here. It has a decreasing interval, right? It's this interval right here. So I'm going to write that when x is between 0 and 2, right? That is the only time in this graph that it is decreasing. Our last concept for today is even and odd functions. A function f is even when f of negative x is equal to f of x for all x's in its domain. The graph of an even function is symmetrical about the y-axis. So even functions are fairly easy to see because they are symmetrical about this y-axis right here. Right? We see that this graph would fold across and match up on that y-axis line. Mathematically, we can check that, and we'll see that a moment in the example. Function is odd when f of negative x is equal to the opposite of f of x for all x's in its domain. The graph of an odd function is symmetrical about the origin. One way to recognize a graph as symmetric about the origin is if it looks the same after a 180-degree rotation about the origin. Right, so if I rotated this 180 degrees, we would see that we get the same graph. On the next slide here, we're going to solve some of these mathematically. Right, so for even and odd, we check out f of negative x. Right, and I didn't do a very good job of putting my negative in there, but I'm going to swap all my x's for negative x. Right, and now I'm going to simplify. Right, so f of negative x is equal to, well, negative x to the third, right? Negative x times negative x times negative x. Two negatives are going to make a positive. That third negative is going to go ahead and make that whole thing negative. And then here, the negative 7 times negative x is going to be a plus 7x. Right, so now I need to determine if this f of negative x, right, I need to determine if it is the same as the original, right? So just a quick reminder here for even f of negative x is equal to your original function. And for odd, f of negative x is equal to the opposite of your function. Right? So I need to go through and see, does this equal my original function? Right? Does this function right here equal to my original function? And no, it does not. And there should be an x right here. But it does not, right? Because my signs are all flipped. And when I have flipped signs, that would be odd, right? So this function is odd because all of my signs within the function have been flipped. So for example, B, let me change colors here just because things are going to get a little crowded. What I need to do for example B is check g to the negative x, right? So I am going to put negative x to the fourth plus a negative x squared minus 1. Right, so I'm going to go through and simplify everything here. Right, I know for negative x to the fourth, well, negative x times negative x is going to give me a positive x squared. And then I do that again, right, because it's to the fourth. Negative x times negative x times negative x times negative x. I have 4 negatives. So that's going to end up back as a positive x to the fourth. And then negative x squared here is going to be 2 negatives are going to make a positive. So plus x squared minus 1. And so what I have done here, after going g of negative x, I am back at my original function. So that makes this one even. And let's check the last one. H of negative x is equal to negative x to the third plus 2. So h of negative x. Well, negative x times negative x times negative x is going to give me negative x to the third, and then the plus 2 is going to stay. Right, so this is not even because it does not match my original function, right? This is a negative x to the third, and my original h of x is positive x to the third. And it is also not odd, right? Because negative h of x, for it to be odd, right, we would take that original function of x to the third and make everything negative. Negative x to the third, and then that plus 2 becomes a subtract 2, right? Everything has to be opposite for it to be odd. And again, this is not what we have here, right? So this one is not a match. So this would be neither, right? It is not. It is neither even nor odd. So lots of vocabulary in this lesson. Lots of relying on Desmos. So that should be enough to get you started on your 4.8 assignment.